In order to capture an object in motion moving with constant velocity, I went to a traffic light in Atlantic Station and recorded a car moving with the same speed in the same direction as it passed by my camera beneath the stoplight. The duration of my video is about 2 seconds, and this chart is a linear graph plotting the constant change in position for the duration of the time of the video. I can then use these quantities under t for time and the x position, the car's position along the x-axis, to produce average velocity and my quantities using Newton's second law. I can now use the graph and data collected from my observations in order to calculate the initial position and the initial velocity for my code that I will explain later on. I'm going to use both the time and position from the first frame of my video and the second frame of my video in order to calculate average initial velocity. As you can see, I've used that second quantity for position, so 0.433 meters minus the initial position, negative 0.183 meters, divided by the second time frame, 0.033 seconds minus 0 seconds, in order to get the initial velocity of 18.667 meters per second. This also lists my initial observation time and my final observation time, which will be plugged into my quantities in my code. This computational model shows the predicted position versus time compared to the observed position versus time, which was analyzed in my video. In order to do this, I included the previously found initial position and initial velocity into this particular part of the code, and I calculated the approximate mass of the car, which was 1,595 kilograms. I then inserted Newton's second law in order to predict the new velocity and predict the new position. So I have the final velocity equals the initial velocity plus F net times delta t divided by the mass of the car. And then I have the final position equals initial position plus ball.vel, which is the final velocity, times delta t. Now, the F net, the net force, is equal to 0 because the amount of pushes and pulls collectively cancel out in order to equal 0. That way you have a constant velocity. When we run this computational model, we get the graph showing the constant change in position over time, which means that there's a constant velocity. This graph shows the difference between the predicted position versus time from my computational model and the observed position versus time from my video. This red line is from the predicted position versus time from my computational model, and as you can see, it's a very straight, constant, linear line. The blue dots indicate the observed position versus time from my analysis video, so each dot indicates a frame of the video. And as you can see, it varies from this line a little bit, but for the most part, we can see that it agrees with the predicted position versus time video from the computational model, which means that our calculations by using Newton's second law were correct.